In the last video on shear forces in beams, we looked at how to calculate the shear forces at individual points along a beam when the beam is subjected to point loads, to reactions, or distributed loads through its own self-weight, and we developed the general equations that describe the shear force at any location along the beam. Representing shear force in beams algebraically is very useful as it allows us to plot a shear force diagram to visually identify locations of critical stress in the beam. Often, it's not possible to express the shear force along the beam using a single equation, but multiple equations may be needed. This occurs when the shear profile differs along the beam due to the different forces acting on it. In general, the number of equations that is needed is equal to the number of forces acting on the beam. In this example, we have a beam with a uniformly distributed load across the entire length of the beam. And because it is supported by two supports at its ends, these supports produce reaction forces. So, in this example, we have three forces, Ra, Rb, and the total load of the UDL. Thus, we require three equations. These equations are determined by adding up the total force at the point where the loads are under static equilibrium. The first force occurs at the start of the beam, which we take as the left end of the beam, and this force is the reaction Ra pointed upwards. At this point, there is no UDL yet, so there is no downward force from the UDL. The beam has to produce a shear to balance Ra, so the equilibrium equation is Ra plus V equals 0. Rearranging this gives us V being equal to the negative of Ra. So we can see the shear force at support A is equal to the magnitude of the force but points in the opposite direction or downwards. Now we move beyond the start of the beam to some distance x from the start such that x is between 0 and the length of the beam. At this point, there are two forces. There is Ra pointed upwards and there is a load due to the UDL pointed downwards. So the equilibrium equation at x is equal to Ra minus the force of the UDL up to x plus the shear being equal to 0. The total load due to the UDL up to the distance x is equal to the UDL multiplied by that distance. Go back to the previous video on calculating shear forces along the beam if you've forgotten how to derive this. So shear along the beam due to the UDL is equal to the UDL multiplied by the distance minus support A reaction. If the total load at x due to the UDL is greater than Ra, then the net force is downwards and the shear force will point upwards indicating negative shear. However, if Ra is greater than the load of the UDL, then the shear force will point downwards indicating positive shear. Now let's move all the way to the end of the beam at L. At this location, we see the third force, which is a reaction due to support B, which is pointed upwards. So the equilibrium equation at the end of the beam now includes Rb. And so the shear at the end of the beam is equal to the total load due to the UDL minus the reactions from supports A and B. This should bring the shear force back to 0 since Ra and B support the total load of the beam. Now that we've got the equations for the shears, we can plot it on a shear force diagram. In this diagram, the horizontal axis represents the distance along the beam, taking the left end of the beam to be the origin and going from left to right as positive. And the vertical axis represents the shear force. Starting at the left end of the beam with the first equation, the shear drops from 0 to minus Ra in response to the first support reaction. The magnitude of this drop is equal to the magnitude of Ra. It then gradually rises in response to the downward force due to the uniformly distributed load of the beam until we get to the end of the beam. This rise is a straight line as a function of distance and is proportional to the UDL, with the UDL being the gradient of this line. Finally, we get to the end of the beam where the shear drops down in response to reaction at support B, bringing the shear back to 0. The normal sign convention is that a shear force that reacts to an upward force is called positive shear, and a shear force that reacts to a downward force is called negative shear. So the normal convention for drawing shear force diagram is to flip the graph and the algebraic results. Now the slope of the UDL is negative. Now let's have a look at the case where there are point loads only. Let's consider a massless beam with 2 point loads, F1 located at distance x1 from the start of the beam and F2 located at distance x2 from the start of the beam. In this example, F2 would be greater than F1 in magnitude, but they both point downwards. The supports must produce a reaction at the support locations given by RA and RB, such that the total force upwards is equal to the total force downwards. So what would the shear force diagram for this example look like? We saw from the first example that point forces produce a sudden change in shear force equal to the magnitude of the point force and in the same direction. So at 0 meters, the shear jumps from 0 in the upward direction equal to the magnitude of RA. As we move from RA to F1, the shear remains constant as there is no additional force for it to react to. When we get to F1, the shear suddenly drops in a downward direction with a magnitude equal to F1. Between F1 and F2, the shear remains constant as there are no additional forces. When we get to F2, we get a sudden drop as the shear responds to the addition of F2. The magnitude of this drop is equal to the magnitude of F2. Between F2 and the end of the beam, the shear remains constant as there are no other forces in this space. Finally, we get to the end of the beam where the shear changes to the upward direction in response to RB, taking the shear back to 0. In summary, it's possible to derive equations for the shear force diagram along the beam, and from these equations draw a shear force diagram. For point loads and point reactions, the change in shear is sudden and is represented by a vertical change in the shear on the shear force diagram. If the point force points upwards, then the shear force is positive, and if the point force points downwards, then the shear force is negative. When there is no load, the shear remains constant, and where there is a uniformly distributed load, the shear changes linearly with the UDL. If the UDL points downwards, then the shear will have a negative gradient, and if the UDL points upwards, then the shear will have a positive gradient. Here we have only looked at uniformly distributed loads and not distributed loads that are not uniform or are more complex.